Just sit back and listen. Put your feet in the ground, in the sand, the dirt, the water, and listen. Listen to your environment. That's what life's all about, guys. Things are tough these days. Times are stressful. The things that haven't left us to stay constant are the sounds of nature. And hello, my fellow YouTubers! This is Roy back again, and I got a great one for you guys right now. What are we gonna do? We're gonna listen to Ed's wheel. Let's hear it make a sound. And we're gonna do that by going through the PMH. And this time I used these Germanium diodes. I set it up as a full wave bridge rectifier. So we're coming in on the two ends of the wire into the AC's poles, and coming out of the DC poles, we're going into the speaker. Let's get this party started. So we're going to start off turning the wheel, and the speaker is vibrating. No, it's not vibrating. We're going to connect this and listen. Low amplification with the capacitor. Sound. We can now take Ed's wheel and we can create sounds. They say in some of his writings that they heard a screeching. So that, what do we have to do to make these screech? That means we would have to go down in capacitance, because capacitance is pretty unique. The capacitance creates a lag in general. And when it does that, it sort of punches a hole. In a sense, punches a hole, only because it creates a time reference. So the lag and the time reference is what the capacitance is in depth-wise. Is it 1 farad, half a farad, 500 farads? These guys right here, and these are 1 nanofarad. Everything's in thousands. It's crazy. 1,000 nanofarads is 1 microfarad. Go 1,000 below nanofarad and you have picofarads. So capacitance, if I break this down and go smaller, we'll get higher pitch. That's what I like about my buddy Tesla. He talks about that higher pitch. Look, still has a little juice in there. You heard that in the speaker. Interesting stuff. Because listen, I'm trying to show you guys how I came about scalar waves and the things that scalar waves can do. Not just going to throw it out there in one shot, but I'm going to say this. I'm going to show you how I learned through the process of electromagnetic and electrostatic. We're going to bring in 15 videos from now where electrostatics and electromagnetic in a canceling scalar wave will reproduce itself upon itself. And when it does that, it takes the object, like an old video I made, where I took, I came up with this pole and I put a winch, this guy right here, and I put boulders on it. And on the bottom side of the winch was the PMH. And what I was just showing was magnetism held up the big boulder. And that's that, not woolite, it's coquina. Very heavy stuff. But anyway, probably 10 times heavier than Ed's product down in Coral Castle. That's why they call it woolite. It's real light. But anyway, so with that old video I did, I kind of just did it to show magnetism can hold up. And, you know, the coils got hot. You're connecting 12 or 24 volts, whatever it takes to hold up that weight. And I was just showing up a little bit about magnetism. A lot of people look at it like it's not levitating. Of course it's not. It's not even floating. But the fact that it's there and I could drop it, bam. I can't pick it up. I got to get it up, set it, magnetize it, then let it go. Here, with scalar waves, it's the opposite. Whatever it is, piece of metal. I mean, we could take that piece of metal right there today, and you just go on YouTube and you can see how they can heat this up with electromagnetic induction. You can heat this up, get it hot. You can melt it, so that means you can disintegrate it in parts. So yeah, but nobody can really take any object and make it bounce up in the air. They can take certain objects and bounce up in the air, but you're dealing with aluminum, you're dealing with iron, you're dealing with electromagnetism, you're dealing with AC waves, and then you're dealing with a DC wave. This is not about that, but that's all cool ways how we learned as students, all of us, on people, Lathwaite and people like that, doing stuff back in the day, and Tesla, Lathwaite, Steinmetz was just crazy. Heavy side, crazy. Things these guys. I mean, my brain's dead compared to all the people I can mention. But so, with that all being said, back to here, you got the capacitors you can change. So we can change the pitch that's coming out of the speaker by changing the capacitance. And then you can see how we amp it, that we can get something to come out of it. So, I guess the next thing we would want to learn, which I would like to teach or put out there, is how to talk into that. So basically, if I take another speaker, acts like a microphone, and talk into it, it comes out there. We already did a couple things from the last video, and we talked about before that, the two videos on scalar waves, the human body, DNA. Here, we're going to start branching it out now into the, I'm going to call it electric universe. So it's the electric part of everything. We're not dealing with gases, so forth. We're not dealing with plasma, so forth. We're not dealing with moisture. That would be the third thing, because we're going through all that and we're dealing with scalar. And to get to scalar waves, you got to have a balance in between two. It's almost like a figure eight, and in the middle there's a void, in the equator. In the middle of my fingers is the equator. There's a block wall, they call it, or something that allows the poles to kind of turn around and go back at each other in the opposite ways, and it creates what we call the Coriolis effect. And that Coriolis effect sends, it kind of gives it this boom, boom, this way. And when you look at Ed's PMH, it's doing the same thing, but it's getting caught up. You got the keeper bar on. What's really happening? Well, a couple things. One is that the energy is running wide open through the iron. And secondly is, if you direct it out of the coils, put a load on, just like this, all of a sudden now it's going to pull from it at intervals. Now, what intervals we're going to pull from it really matters on the capacitance, because I don't really have the setup right here, but on some of my studies I'm doing, is if I had on these two wires a LED in between these wires and an LED between these wires, they both light up. If I add capacitance to one side, this light lights up differently in frequency than this light. So that goes ahead and shows all you guys the fact that capacitance will go ahead and lag the time frame of how long does it take to fill this with the energy that's coming in, the induction. All matters. There's a lot going on here, but it goes to show you that when you deal with capacitance or underneath the capacitance, what you have here is a full wave bridge rectifier. So now we're taking the energy that's flopping, it just in, out, in, out. It's coming from both sides. So both sides of the ends of this full wave bridge rectifier is noticing a push every other stroke. So every half cycle gets a push. So there's two pushes to one. So ring bell twice, Ed says, right? So he was talking about that. So that matters here, how it all of a sudden you get electromagnetic reaction going here. We'll call it transformer action. And then you go touch. Now if I just leave it on there, it's vibrating. You're not going to hear nothing. So to sound, a pressure wave is the fact that it's rotating. So that means you need to take the fluctuation of the two poles and the reaction of the transformer action. You need to have another oscillator that goes to the speaker for voice or for whatever you're going to put out of the speaker. So if Ed was to have it make a noise like that, he had to find not only a frequency through sound, but he had to really know the sound to create that frequency through capacitance. Leave your comments. Hopefully you guys enjoy the little tidbits. I'm going to keep working them for you, because what I really want to show you, I just can't put out now. But I got to show you in increments, so it's out in public, of what every step I took in my sabbatical to get, this has got to be 85 to 115 pounds. It's crazy heavy. To get that to just sit up, it takes Ed Leedskalnin, Tesla, Dr. Korsky. It takes crystals. It takes a steady frequency. It takes longitudinal, but really not longitudinal. They're scalar waves. And it also takes a constant static. Static is everywhere. Everywhere you look around you is static. That's why sometimes you'll get shocked by touching something, walking on a carpet, yada, yada. It all depends on what pressure you're dealing with in your environment. But at a certain point in your environment, it's gonna get colder and the air dries out, less moisture. You're gonna get a static presence. And with that static, if you were to add a scalar wave, you would be able to tap into any object at different frequencies. But at any other frequency you're tapping in, and that's what I was just showing you here. It's more about the harmonic of the frequency, because they don't go 1 for 1. It could be a 10-to-1 ratio, 20-to-1 ratio, 50-to-1 ratio. It can be whatever ratio, because basically phasing is what it's all about. And to be out of phase, at the opposite out of phase, you can be at any phase itself and be the opposite of it. So you have to know a full spectrum of where to be researching and where to be knowing where you need to pay attention. So phasing, electrostatics, very important. And the other critical thing is with crystals, you can hold a steady frequency. And with steady frequency, once you find the harmonic of the frequency that the product is made from, meaning the atoms, the molecular structure of the atoms, whether they're sitting in a figure 8, sitting in a 6-pack, 8-pack. And what I mean by that is when you get into atoms, you can see what their lattice is about, their molecule structure of the atom. And when you have, whether it's iron, whether it's plastic, because plastic is really just a couple things together. And then no matter what the material is, that once you have a tone, that's what Ed was great at. He had the little sound room, and he would tone things. Like, so if you take this piece of metal, there's a sound. What does that tell you? Hit some magnets. Let's hit a south magnet. Same sound. Let's hit the iron. Let's hit the wood. Everything's got a different sound. Wood with metal. All right. So let's hit Ed's PMH. Wow. So if I was a betting man or educational man, like Ed says, that would investigate in something, is when I hit that, there was a frequency that was a vibrating frequency to my ear. Everything else had a dampening sound, meaning that it was connected to something else. There was other things going on. It takes a lot more research to find out exactly that tone. But you get here, what you got there is a resonating frequency. It's due to the space that's in between the material itself and how much it's still going. It's still doing its harmonic thing. So that length of not only the time it takes to go a certain distance from one probe to the other, that gap, but the time it takes to come back. So there's your Ed ring bell twice. And that goes to a lot of stuff. Ring bell twice, meaning that is the length of wire. So the distance out, arms reach out, also has to be our arms reach back. And then you'll have a cycle. Yeah, you can have a half a cycle or a full cycle. And that's your cycle. And you can break that up in quarters, eighths, sixteenths. And you can call each one of those is there's the whatever the cycle was on that length to go out can be broken down coming back in a sense. So that means that you can have nodes or overtones, and what you can do there is you space out how many times that sound wave, pressure wave, will collapse within itself in the center and then release itself back out and come back into itself. So pretty much you're dealing with a pressure wave from sound, what we just did right there, and then you're dealing with the length of the frequency, and then you're looking at the divisional on how many times you can create overtones or nodes in that, and then you can find a harmonic. And that's what I mean back to Ed, what I was talking about here, is that if you're dealing with Schumann or something of a element, iron or whatever, you're dealing with items that have a true resonance about themselves, and pretty much from there you can sort of use sound to kind of get a grip of what the frequency is, to tap into that sound. And once you match sound together, you're in the frequency range, and you ballparked of what that frequency is. Now, if you can't accomplish that frequency, you can go down in quarters, eighths, sixteenths, and develop these nodes, you can call them, or you can call them overtones. And at this point becomes a cymatic. It becomes something that is part of a bigger picture that still is in resonancy of what is going on. So basically, if you walk on a train from a train stop and everybody, you look down the train, there's the people getting on the train. They're all different places and different times. So not one person at one time walks on that train together without being in a reference difference of where they're standing or a time difference of when they walked in. You guys, leave your comments. Sorry to overtalk. Didn't want to do that. Pretty much leave your comments. Hopefully you enjoy. Peace out.